Okay. Awesome. Okay, so now we can start talking about the real main interesting stuff in the course. So I named this as interpretation of probability Bayes rule. So I will start talking about like the contrast between Bayesian and Frequentist. So I think most of you are probably most familiar with Frequentist way of interpretation of probability. So I will talk about both and then introduce you Bayes rule in this section. All right. So you probably, if you have taken like 341 or 240 or 141, and 242, I guess, last year you will probably have heard about or have done significant tests and confidence intervals. And those ones that you have done before are mostly classical frequentist inference. So these are based on central limit theorem and the law of large numbers, all of those. And however, so this is the mainstream for a while. Even now, I would still say the classical or frequentist inference still the mainstream. But there are certain situations that actually the classical or frequentist inference might not be adequate. So, and that's where actually Bayesian methods is worth learning and study and then put into practice. So let me give you an example. Suppose you flip a coin and you don't know the probability of heads, so heads and tails, and you flip it 3 times and gets tails all 3 times. Okay, so you don't get any heads. So now, if you're curious about the probability of heads, which is you didn't have it, right? So in this particular experiment, you do it 3 times. What you get is the sample percentage of heads is 0. Okay, but do you think it's an accurate estimate of the true percentage of heads? Why not?
Because they're independent flips.
Yes, that's true. Yeah, they're independent. There's that. But we do see 3 independent trials and get all of them heads, get all of them tails, right? But what about heads? Yes?
Because we think there should be an equal likelihood of something of the coin falling heads versus tails because it's symmetrical. The object.
Yeah, so there's that. So that's the part that I put it on the 3rd bullet point over here, because if we know that it's a fair coin, then it should be 50%, right? And then how to incorporate that information or that belief in the inference, that's what Bayesian can come into play, right? Okay, good point. But another thing I want to mention over here is that you only flip it for 3 times, right? I guess the natural thing to do next is you flip it for more times. And then with law of large numbers, in the end, you will have 50%. Like the sample percentage of heads should, if it's fair coin, should be around 50%, right? Whereas over here, we only do it for 3 times. So this is a small sample, and we all know that small samples have a lot of issues when you're trying to do inference. Right? So that's another, I would say, a drawback of thinking about probability or making inference through the classical frequentist inference. But then, as what's your name again?
Sahim.
Okay, as what Sahim pointed out, also because if you know a priori, so you would see the terms pretty often later on, right? Yeah. So you probably heard that in Bayesian inference we have prior, we have posterior. So it's just prior itself is just the name. I mean, the meaning of the English pretty much tells what it is about. Is before you do any kind of experiment, what you think of the hypothesis or whatever that is. So for us in this case, if we know that it is a fair coin, so even before we're flipping the coin, we will think it's 50%, right? But if we just don't incorporate that at all and see 3 sample draws and then see all of them are 0, all of them are tails, then we're not able to incorporate any of the information that we know beforehand. And this kind of information is actually pretty useful if you think about it, right? And again, actually frequentist inference and Bayesian inference in the long run, in the sense that if you do the experiments long enough, those are going to converge. Like Bayesian inference is going to converge to classical. Yeah, so like what we were talking about earlier, 3 flips are really small, right? If you do it more, you're going to get 50%, right? So that is the idea that the large sample, et cetera, those assumptions, and then the Bayesian inference, if you have experiments long enough, that's what we call data, right? You have the prior, and then you incorporate what you see, and then you arrive at something called posterior, and that in the end will converge to the frequentist inference as well. Okay. So for this example, I'm just hoping to give you an idea in what situation that frequentist methods might not be adequate. And in particular, when you have small sample size, that's always the issue. And then you will see that with Bayesian inference. Of course, the larger the sample size, the better. But Bayesian inference can work even if you have a super small sample size. Okay. And again, another thing is about the prior information, what you want to incorporate, what you want to use. And you might think, okay, it's just flipping a coin, like that idea of 50% might not be a big deal. But in a lot of other studies, some kind of like say previous experiments or previous like scientific studies, you really want to use that information to make your new inference. So that kind of information, I would say, because this is a toy example, but in those examples, you will see how useful they can be when you're doing your Bayesian inference using some expert knowledge or previous study results, et cetera, et cetera. So we'll see examples of that. But I do want to raise it up that small sample size cannot work well with classical inference. And then classical inference or frequentist inference does not incorporate any extra information that you might have. So this is what we want to do with Bayesian inference. And then the Bayes rule will be able to allow us to do that. So you will see it in a minute. Okay. Okay, so the name is actually, Bayesian itself is from a mathematician and a minister actually in the UK in the 18th century. So his name is Thomas Bayes, and then later like Bayes rule, blah, 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 and then whoever believes in Bayesian methods, I couldn't use the word, whoever thinks in this way is called Bayesian, okay, and then everything is called like Bayesian methods, et cetera. So that's how the name started. But back then, it was actually for 200 years, it wasn't developed well, because later you will see that even though you can do some toy examples with Bayes rule, but if you really want to make inference in real applications, you have to rely on a lot of computation powers. And that's why didn't like the whole field didn't develop until I wrote over here around 1990, because that's the time that the Gibbs sampler was invented. And then that's why now we actually all be able to write our own Gibbs sampler by coding it up in R or Python or whatever language that you like. And so I'm using this as a, I guess, a justification in a way that computation is really important in Bayesian methods. And I think maybe for some of you might be a little bit difficult to start with, but once you get the general idea, the more practice that you do, the better you will become in terms of doing Bayesian inference. And so for these 3 points over here, let's just go over it really quick. So the good features of this is for modeling perspective, you can incorporate prior belief or domain expert knowledge. That's what I was talking about earlier in the Bayesian inference. Theoretical, but also I mentioned it earlier, it doesn't need large sample assumption. Even if you have small samples, you can do inference. Whether it's like accurate or not, that's a different story. But it's more about you will be able to, in a way, get away with small sample if you only have small sample. In a lot of experiments, that's what you have, like chemistry, I think, biology as well. And then computation, like I said, it's the general frame, like we call it Markov chain Monte Carlo and MCMC for short. And so in it, there are other like different types of like MCMC techniques, like Gibbs sampler, etc. So we're gonna talk about that as we go along the semester. Okay. All right. So anybody knows about Nick Silver? So he is a statistician. In particular, he was a Bayesian statistician. He started off doing really well predicting baseball games in the 2000s, I think. And then he started doing prediction for presidential elections, and that's how he became really famous in a way. And he has a website called 538. So yeah, for 2020 election, you might want to check it out. But anyway, so he used Bayesian approaches or Bayesian methods to do his prediction. And in 2008, the presidential election, he got 49 out of 50 states correct in terms of that plus DC. And only missing Indiana. And for 2012, he got 50 out of 50. And you might be wondering what happened in 2016. And I remember that I checked this, and I think because if you were following the news at that time, you will see that, like, I guess you remember, like, beforehand, everything is towards Hillary Clinton, blah, 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 blah. And then as the election was going on, people start to change their prediction and blah, blah. So the final stuff that I can get, say the final prediction on that morning that Nick Silver did, so he had a 71 chance to win, he predicted Hillary Clinton has a 71 chance to win the presidential election, but you have to see it like to the other, like compared to the other predictions, right? So he was still doing relatively better than the other ones. But again, I mean, we're not able to go into details of the methods, of course, but by the end of the semester, if you're curious, I think you'll be able to start to understand how he was doing his predictions. Okay, so he was using Bayesian, I think, spatial models to consider all of the relationships among within the state, among the state. All right, so I was talking about the two schools of statistics for a little bit, but let's just put it together side by side, and I think that would be a good way for us to make the contrast, what we're trying to do in the Bayesian paradigm. So on the left is the frequentist and classical, and it relates the way that people think about probability is the long run relative frequency of repeatable events, right? So if you, in your probability course, you probably have seen this equation before. The probability of event A will be the limit of n goes to infinity, and you divide it by n, right? And then on the top is the how many times A happened, right? And we really have to have n goes to infinity to get a good idea of what the probability is. And again, as you can see that the definition over here, you have to do repeatable events, right? You have to repeat the same thing multiple times. That's a really strong assumption. And you have to round it super long, and it's a relative frequency, okay, by doing the ratio. Okay. Yeah. So again, I put it down over here. What if you only have one-time events, right? What if n is 1? What we saw earlier in the example is n was 3, and then like the number of A was 0, right? So we get a 0 over there. But it wouldn't be a good sensible, actually not, that wouldn't be a sensible guess of the true probability. And then of course the small sample size. So if we go to the Bayesian paradigm on the right, we like to say that Bayesian way of thinking about probabilities is subjective. Okay, so earlier we're talking about flipping a coin. That's pretty not subjective in a way that if the coin is fair, then it's objective. But it's actually useful for us to think about probability in a subjective way in terms of Bayesian, because you really say for probability of events A, like two different people might have two different beliefs about this. And then that actually you will see that sometimes what your prior belief, like the PA, actually going to affect your posterior a lot if you have like vastly different things. And what you're going to see down here is, so I circle here Bayes' rule. We call it Bayes' rule. And so A, you can think about event, but a lot of times in actual Bayesian inference, we think about it as hypothesis. Okay, what's your belief about something? Okay, and so this is prior, and we're going to be collecting data, like I said. You're going to keep flipping, and then you're going to keep updating what you think the probability of heads is. And then here, for the notation, I use B as data over here. Okay, so as you can see, for Bayes' rule to work, it's nothing too fancy, actually. It's conditional probability, right? So if you remember from your probability course, the event, or the probability of A and B both happening, right? You can do it in two ways, right? One is if you have the marginal of A times the conditional of B given A, right? That's what we learned before. And that's what you see on the numerator over here, right? But you can always also go back to the other direction, right? You can do times conditional A given B, right? And that's what you see over here, right? So we put Bayes rule, like typically we put in the way that I show in the slide, because later you will see how we can compute those probabilities. But overall, it's conditional, marginal to become the joint, okay? So, but the thing is here, let's think about the interpretation a little bit more. Let me clear this and then talk about it. So we know that mathematically this works, right? But what does it mean when we put it in the Bayes rule like formulation over here? So earlier I was saying that you can think of A as a hypothesis, right? And I was saying that B is what you see in your experiment. We call them data, right? So the Bayes rule, this formula is really telling us that we start with what we know before we collect any data. And then we are able to incorporate what we know, what we collect, which is B, and we actually gonna have some model for this, in order to make it work. And then with what you have before, and then with what you have in your data collection, you'll be able to come to something we call posterior. That it's a conditional probability of the hypothesis A given what you see in the data. Okay? So I think that's the key point of why, like say, it makes sense to put the Bayes rule in this way. It's really about, now I'm trying to have some idea about a hypothesis. Okay? Before I do anything about it, which is PA, I have some idea. We call it prior or a priori. Okay? And then you're going to collect data. And it's usually expressed in the model, and the model is being expressed in this way. I should use a different color, sorry. Yeah. So the model, usually it's a parametric model, so you'll be able to specify what is B given A. We're going to talk about example in a minute. And then the key idea is that with your prior PA, and then with your data B given A, you're able to arrive posterior. And the posterior idea is that now I want to sharpen my belief about the hypothesis after I get the data. So that's how you think about the conditional. Okay? So conditional probability, we learned it before in other courses, that say for B given A is, given A is true, what's the probability, or given A happens, what's the probability of B, right? So that's the model that we're gonna learn. But then at the end of the day, we are curious about the hypothesis itself, right? So now the conditional probability, like we see it over here, is A given B. So to interpret this conditional probability is that given that we see the data B, what's our belief about A now? Okay? So this is the general procedure of doing Bayes inference. The simplest form is what we see right now, and I will give an example of how you can do it by hand if you want. But later on, when we move to more sophisticated Bayesian models, it's still based on this Bayes rule. Okay? You're always trying to combine your prior information with your data to arrive at a posterior, and the posterior is really reflecting your sharpened belief about the hypothesis when you see more data. Okay, so you might be wondering, okay, now we understand how things work for this, but how are we going to compute this PV? So this is usually like the hardest part, and that's how the computation can come in to help us. So you will see in a minute, we're going to do it later as well, that if you have a partition of A, then the margin of B let me finish writing and then I can talk about it. Let's just say a partition of A1 and A2. Let's say just two of them. So this is A1, and A2. Okay, it's a partition, so it combines to be the whole thing. So if I want to know, this is also like a quick review, I should say, that if I want to know the marginal probability of event B, I can look at the margin of A1 times the conditional of B given A1, and the same for A2 and B given A2. Right? And the reason why it works, sorry, let me write it over here. The reason why it works is because this joint, this becomes the joint of A1 and B, right? So that's A1 and B. And the second one is A2 and B. Okay? And because this forms a partition, you get the whole B. So this is the simplest case, as you can see, how we can compute PB. If the question is really simple, that we'll be able to do the partition and compute everything. But of course, later PB can be complicated, and that's how the computation techniques that we're going to learn can help us finishing those. Okay? But keep in mind that Bayes' rule is nothing fancy. It's just a bunch of conditional probability, joint probability, and marginal probability. But it's really being used in a smart way to help us to think about how we incorporate data into our hypothesis. Okay, you start with the prior. Sorry, I just repeat it again. You start with the prior. You get the data, which is through a model. So it's conditional B given A, and then you arrive at the posterior. Okay? Posterior is always conditional, and it's always conditional on the data. And that's what we want, because we want to sharpen our belief about the hypothesis as we get the data. Right? And something you will see later as well is the whole updating can be sequential. Right? Say, let's go back to the example that we said earlier. If you flip a coin, let's do like a Bayesian inference of the flipping coin example that I was doing earlier. Okay. So earlier we were saying, what is it? Has and tells, right? And we did 3 flips. And what we have? We have, among the 3 flips, 0 heads, right? And 3 tails, right? I think that's what we have. Okay? Yeah. So forget about the classical because it wouldn't work in this case. But if we think about the Bayesian inference over here, our prior, if we think it's a fair point, is the probability of head should be 0.5, right? Mm-hmm. Yeah. So let's define, let's define the outcome as event E. Okay? So what we do here, so the prior, before we do any kind of experiment, is 50% for getting head, right? And naturally, remember the posterior, like the Bayes rule, what we want to have is now we get some data, right? So conditioning on the data, conditioning on the experiments that we do, what's our belief about H now, right? So if you follow the Bayes rule that I showed you earlier, this will be the complete formula for this, right? So what does it mean? Now we know that a priori this is 50%, right? And E given H, we would better put a model on this. And if you guess the appropriate model for this, if you think about it, because you're doing independent flips, right? And it's binary outcome, so it's natural a binomial distribution. We're gonna see the example soon, but I do want you to talk about the smaller example over here. So the model later, as you will see, we're going to use is a binomial model, and then you can compute those binomial probability for different events. And then at the end of the day, you'll be able to arrive at this, that given that I see 3 tails out of 3 flips, what's my probability of H? Okay? So I can guarantee you it won't be 0, because we started from 0.5. It's going to be some kind of computation involved that will be less than 0.5 for sure, because we don't see any tails or any heads, right? So you start with 50%, I think it's going to be 50%, but for 3 flips, I don't see any of them. So naturally, when you incorporate your information in the inference, the probability, which is the posterior probability, it's going to be smaller than 0.5, right? And if you keep flipping, let's say you keep flipping for 7 more times, and let's say all of the 7 times actually got tails again, and I'm sure you can, so at that point, this is what we call sequential updating. You're going to do a second round of this, and this probability is going to be even smaller, right? Because you don't even see any of them being appeared, right? So that's the general idea, that we start with the idea of something, some prior belief about some, so this is a hypothesis, obviously, and then you start to collect data, and then you use the data to sharpen what you believe. Okay. So for in this example, we have the heads to be 0 and tails to be 3. And earlier I was saying, if you keep flipping, we still keep getting tails, then it's only natural that the posterior probability that you're going to have is going to be keep going down. And then the more you do, it will keep going down. But of course, if it's a fair coin, you would never really see like 10, I think. Oh, you still have the chance, but it's really low chance to have 10 tails out of 10 flips, right? Yeah, so that's the way that you can see that. In the long run, if you imagine what you're going to do, in the long run, we will actually, if it's a fair coin, I'm pretty certain that this is going to be converging to 0.5. Because you do it like you get tails, heads here and there, the sequence, and that's going to converge to what the frequentist way of thinking about the probability, which is 0.5 if it's a fair coin. Okay, so this is the general idea, and I do have a better example, I think, for this. So let's get there and talk about it. Let me just show you over here. Yeah, don't worry too much about example 1. I think it's probably repeating what I was talking about earlier. But I do want to talk about example 2 over here a little bit, because this is another biggest difference between Bayesian and frequentist. So I'm sure everybody heard about confidence interval, right? And when we talk about 95% confidence interval, let's say of an unknown parameter, I guess let me put in the context, let's say the mean number of, like the average number of courses you're taking this semester, let's say. We want to know about that unknown parameter theta. So if I get a confidence interval of, let's say, 3.2 to 4.6, suppose, okay, 95% confidence interval. Well, how would you interpret that? And down here, I wrote one more sentence. Is this the interval that has probability of 95% of containing theta, or is it something else?
So like 95% of the time, that interval is going to capture the true mean.
Good point. Yes. So confidence interval, which is actually a term for from the frequentist inference, is that if it's 95%, is that if you do the experiment enough times, and then each time you're going to get a confidence interval, right? And then that 95% is actually telling you that when you do it, say 100 of times, then 95 of those 100 confidence intervals will contain the truth. Right? It's always tricky in a way to understand what a confidence interval is in the frequentist paradigm, I should say. But soon you will see that for the Bayesian paradigm, when we talk about, we usually use the word credible interval. Like say, if we talk about 95% credible interval, when you present an interval over there, we're really talking about that interval has 95% probability of containing the truth. Okay? So Bayesian inference in this way is a more direct statement of probability. Because the traditional confidence interval, you always have to like say, oh, I have to do the experiments enough times, and then that's how you're doing it, and that's how things are constructed. But Bayesian inference in here will be more natural to understand for that matter. Okay, so I will talk about that in a minute as well, especially why we can use Bayesian inference or say Bayesian credible interval as a probability statement. Right. Yeah, so down here, frequentist is indirectly related to probability of the hypothesis, whereas Bayesian is directly related to the probability of the hypothesis. So if you're a little bit rusty about the confidence interval interpretation, you might just go back to like Wikipedia and take a quick look. But don't worry, that's not the focus of what we do. But you should have known this from some of your other courses already. Yeah. Next, yeah, I want to talk about this. So the procedure of Bayesian inference, I want to go through it with a short example, and you might have to do a little calculation on your scratch paper. So the goal, what we're talking about, is making inference of an unknown quantity, say like mean the average number of courses, for example. So I've been talking about this before. Before seeing any data, someone or every one of us going to have some prior probability, and usually we write it as P hypothesis. So that's what we call this prior. And then you're going to collect data, and then you're going to combine what you have in the data and in the prior to come to something called posterior probability. And we have seen in terms A and B, but in terms of like a procedure of Bayesian inference, you can think of now it's going to be the conditional probability of your hypothesis given what you see in the data. Okay? And of course, you have to do Bayes rule, like all of the details over there. But the general procedure, you start with the prior, you collect data, and then you update to a posterior. Okay? And the posterior is conditional of the data.
So is the prior probability like, sorry.
Mm-hmm.
So it can be a guess. Say, for instance, your code right there, the probability that it would just fall down
Mm-hmm.
magically.
Mm-hmm.
That could be a guess, or it's something that we assume to be true, like a fair coin that we already assume that it's 0.5.
Exactly. Yeah. So for a fair coin, I guess everybody's guess is 50%, right? If you know it's a fair coin. But for some unlikely events or any other events, like people just might have different beliefs, and then that means they're going to start with a different probability for their hypothesis. Yeah. So that said, if two people holding two different beliefs a priori, and then if they see the same data, they're going to come to two different posterior, right? If you do the calculation, because you start with two different P, and even though you see the same data, when you crack the Bayes engine, like what we like to say, like you apply the Bayes rule, your posterior probability of the hypothesis will be different, right? So it's actually super important to realize that the hypothesis, the posterior probability, you need to have the hypothesis in the prior as well as the data. So both of them contribute to the posterior. Okay. Earlier, your question was on, say, two different people, or like I should say, I extended in a way that if two people started with two different priors, and then if they see the same data, they're going to come to two different posterior. That makes sense, right? But it's also possible that it's only me, and I have a prior probability or belief about something, and then I collect the data in one class, and I have a posterior over there. And if I collect the data on another class, if the data are different, then I will come to a different posterior, right? And that all comes together because of Bayes rule, because of how you're going to compute it. So I understand now I'm maybe like talking a little bit like high level, but we're going to see like example of how you can compute it. So you'll see in action that you're going to come to different numbers, of course, but the general high-level idea is that both the data and the prior contributes to the posterior. Yes?
Is it true that if two people start with different prior probabilities and they see the same data, that the posterior probabilities will converge always?
Good point. What do you think?
I would assume yes, but like I don't know if there's like weird situations where they could like diverge or something.
Yeah. So I should say, so this is again another really good question. This is again another thing about how when we say in the long run or in large sample cases that the Bayesian inference is going to converge to the frequentist. So if you imagine, okay, so let's just say, what kind of example I can use? Let's just say the average, like the average number of courses, for example. And okay, say I have a belief that the average number have a 50% chance of being 3, for example. and then someone else believed that had 50% chance of being 4. Okay, so we both start collecting data. Okay, we collect data together, right? So for, say, we collect data from 10 people, we're gonna come to different results, right? But as we do more, if you keep growing your sample size, if you keep doing your collection, then the information carried in the prior are gonna be diminished because now your data are gonna control, right? Yeah, so this is another reason, I should say, justification of why if you have large sample size, the Bayesian inference is going to converge to frequentist, and that's actually a really important research field that people do, a lot of theory in over there, yeah. But I would say, as long as you have large sample size, and then it's the same sample, right, like you keep growing, I keep seeing, oh, you have 5, you have 4, you have 4, you have 5, that kind of stuff, I have the same information, then as I collect more data, my prior are going to be less and less important. Yeah. So this is another reason why you would think, yes, even though Bayesian methods works well for small sample, but if you can, you better get a large sample, right? Because if you have small sample, your prior is going to dominant, and if your prior is not good, you're screwed. Mm-hmm. Good question. Yeah. Anything else? All right. If not, let's continue, because I do want to get that example. So over here, one last contrast between frequentist and Bayesian over here. So you see that this is what we call about posterior probability. That's the Bayesian inference, right? It's given the data, what's the probability of the hypothesis, right? But actually in frequentist, which is what we know about the p-value, is the reverse conditional. Sorry. Where is it?
Other trash.
Yes. Okay. Yeah. So p-value is actually, remember that. So if you remember about the frequentist procedure, like you have to start with your hypothesis, you have the null hypothesis, you have the alternative, and then the p-value is really defined in a way that, given that your null hypothesis is true, what's the probability that you see something as extreme as you see the data? Right. So if you phrase that into a conditional probability, that's the reverse, right? It's given that the hypothesis is true, what's the probability that I see the data? And that's why the confidence interval that is derived from this general idea, like linking to p-value, is not a direct statement of the probability of the event. Okay? It's the probability that, given that the hypothesis is true, what's the probability of the event, right? Whereas what we've been talking about for Bayesian, it's I start with the prior, which is the probability of the hypothesis, I collect data, and then I update it given what I have in the data, and I come to posterior. And in this way, I think it's even a better situation to see why the posterior probability is a direct statement of what your belief about the hypothesis after you see the data. All right, so, okay, enough about frequentist, and let's look at two examples over here that you might want to use your scratch paper a little bit to do it. So a lot of times, especially intro staff, we use this tool example of showing how Bayes rule is done. I still think it's a valuable example, so let's go over this really quick. So there are 3 probabilities over here. One is the American Cancer Society estimates that about 1.7% of the women have breast cancer. Okay? And then somebody doing some study stated that mammogram correctly identifies about 78% of women who truly have breast cancer. So those are the true positive, right? It shows up positively, and it's truly that the person does have breast cancer. And then the last probability over here is what we call false positive, and it's 10%, meaning that among all of the people who tested positive, no, what is it? False positive. False positive is, I think, among all of the people who so true positive is among all of the people who have it, then 78% of the time it's going to be tested positive. Okay, so I think false positive, sorry about it. False positive is, if it's 10%, is that among all of the people who don't actually have cancer, going to be tested 10% chance to have it. So that's a bad result, right? And usually people care about the false positive rate and the true positive rate of the particular test, because no test is perfect, right? So what we want is this number to be high and this number to be low for a particular test, right? The better, like the higher of this, the lower of this, the better of the test result, or like the test correctness or accuracy. Okay. All right. So with this information, you can write it down, and I will show you later as well. So now, so someone walks into the office and then hoping to get a mammogram, and without doing any kind of testing yet, what probability do you think a doctor should assign a random female patient having breast cancer? That will be the probability that we saw earlier, right? 1.7%, because that's what the study tells us, that if I don't know anything, it's 1.7%. So this is the example of expert knowledge. Say, if you know something elsewhere, assuming that it's true, then this will be a good prior probability to assign before you do it, right? Okay, good. So now, when a patient goes through breast cancer, so there are two, of course, competing claims. So what if now that the person goes through the mammogram and have a positive result? What is the probability that the person actually has cancer? So you will see that when I write the question over here, we can actually phrase it even more accurate, that what is the posterior probability of having cancer if the mammogram yield a positive result? 78? Why do you think it's 78?
If a mammogram yields a positive result, that's the true positive.
Yeah, so that's the thing. It's always easy to get confused. I was confused earlier as well. So this 78% is among the people who truly actually have breast cancer, 78 of them going to be test positive, right? But what the question is asking over here is actually the reverse. Because what we care about now is, now I know this woman has tested positive, right? I want to know the conditional probability that, oh, I know she's tested positive, what's actually the probability that she does have cancer, right? So as you notice the way that we phrase the question, you probably will guess that Bayes' rule will be useful because it's a bunch of conditional probability. So now we're just switching from, so remember, let me write it over here. So remember earlier, we saw Bayes' rule in this way. Right, this is what we saw earlier. So you can see that Bayes' rule, again, is conditional probability, some kind of manipulation of that. So you can see that if you know B given A, and if you know margin of A, if you find a way to compute margin of B, you will be able to get A given B. And that's exactly what we're faced here with the question, right? So we started with, so I will put into the pieces later, but it's exactly that earlier. We know 78 is among all of the people who actually have breast cancer, let's say A is that, what's the probability that's going to be tested positive? That's B, right? And now what we want to know is the reverse. We want to know that if the person is tested positive, what's the probability that she does have cancer? Okay? So that's the case where Bayes' rule will come into play, as you might have guessed. So I will show you the general procedure. So introstat, that's what I usually use as an example. So you come up with hypothesis, right, whether to have cancer or not, right? So 1.7% is having it. So 1 minus that is not having it. And then the other two probably is going to come into play in terms of the data, right? So we know that the true positive rate is 78%, right? So that means 22% of people who actually have cancer are going to be tested negative, right? And on the other hand, we know that the false positive is 10%, meaning that if you do not have cancer, you still have 10% of chance of testing positive. And that at the same time means that 1 minus that, which is 90%, is the probability that if you do not have cancer, you have 90% of chance not showing up in the exam. Right? So the important thing over here is that this is a partition, right? This is a partition of the entire population. And all of this is a partition as well, in a sense, right? And that's how you can actually come up with the remaining probabilities to do that. And then when you do the multiplication, you're going to get the joint, right? Say 0.0133 is the probability that you have cancer and you test positive, right? And the same goes for the other 3 over here. And then if you want to apply Bayes' rule, what should we care about? The 4 probabilities, some of them do not matter. What do you think? Which ones matter? Because we want to focus on the cases where the person has a positive result. So which are the 4 are the ones that have positive result? It's the first one and the third one, right? So let me change the color. So we compute all of the joint over here, but we only care about this one and this one because these are the cases that they're tested positive, right? So this, again, going to become our condition because now we're asking the reverse question. Given that somebody's tested positive, what's the chance that she does have it, right? So the Bayes rule is going to tell us that in the denominator, we'll have the probability that the people are actually going to have positive results, right? And in the numerator, we'll only be looking at, let's see, the first one over here. Because the first one is the joint probability that the person actually tested positive and had the cancer. Yeah. So this was the part that we talked about B given A times probability of Barnard of A. And this, remember earlier I was doing some demo partition and then sum them up. So this is getting us PB. And the B is the event that we define over here that is being tested positive. Okay? And because there's only 2 ways that you can test it positive, right? Either you have it or you don't have it. And that's a partition. So that's the reason why we're able to sum them up to get the marginal probability of B. And then in the end, when you combine this 2, what do you get? You get probability of A given B, right? According to Bayes' rule. And in this context, it's going to be, given that you test positive, what's the chance that you do have the cancer? Make sense? Cool. So the answer, I think, we probably need the number. Yeah, the answer now is, the probability now is 12%. So this is the posterior probability. Okay? The posterior, imagine, like keep in mind here that the posterior is after the person does 1 test and the test becomes positive. I should say, the person does 1 test and the test is positive, right? So do you think 12% is a high chance? Still low, right? So, because if you decided that, oh, this person does have it, and then she'll have to go through a lot of procedures and stuff. So a lot of times with the low probability, like 12%, definitely is low, is higher than 1.7, right? Because now the general public is 1.7, and this person tested positive, so naturally you're going to have a higher chance. You will guess the person will have a higher chance of having the breast cancer, and that's how the data is helping you to sharpen your belief, right? But this is the case, I should say, 12% might still not be high enough that you're going to determine, okay, this person does have it. Let's send her to the hospital and do all of the tests or like all of the chemo and stuff. So people might be guessing or might be planning to do another test, right? Because 12% might not be high enough. And depends on the results of the second test, you might have a better idea of whether the person had it or not. So this is what I mean by sequential updating. That just now we came from prior to posterior, right? And the posterior, yes, now we have a better understanding, but still we couldn't make a decision, so let's do another one. And another test is another round of getting the data, right? And now for the second test, as you might imagine, the second test, when you do it, your prior are going to be the posterior that you had before. Because now I already know this person have first test positive. So when I see these results, I wouldn't assign 1.7 to this person anymore. I'm going to assign 12%. Right? And then depends on what I see in the second test, I might have a higher chance that I will assign. If the person comes out to be positive again, I'm sure the second posterior are going to be even higher. And if the second test comes negative, then I think it will be lower, but then of course you have to decide what you're going to do. Okay? So sequential updating is a good feature, I would say, of Bayesian inference, as you can see that you can keep updating your belief as you collect data. Okay? And then for this particular case, it's not that all of a sudden I'm going to do like 10 tests for the same person. I'm like counting all of them all together. For this kind of, I would say, application, it's more natural that you have one test at a time and then decide what you're going to do next. Okay. All right, cool. So this is what I was trying to say. Now, if I'm going to do the second test for this woman, we're probably going to choose the prior to be 12%, because that's what we see from the posterior before. And then if you do another round, so here I'm just assuming that the second test is also positive. Then if you do the same Bayes rule again, and then you will see that now the chance is much higher. And not surprising. And I think it's pretty intuitive in the sense that, of course, I mean, the exact number, it wouldn't be intuitive to have to compute it. It's not that you can guess it, but the general trend makes sense, right? Because now we see another positive test. So it makes sense to think that the person is going to have a higher chance. And that's what the posterior tells you. And that, again, is a good demonstration of how the sequential updating makes sense. And then how, I would say, the trend of the value, like say the posterior probability, how it's going up and down is highly dependent on the data, right? Yeah, but again, if it's 52%, you might want to do another test. I don't know, but I don't know. Maybe there definitely like be a standard practice out there in the medicine community, but I don't know about it. But I just want to show you that if the person gets the second positive again, then the chance of having breast cancer is much higher. Okay? And you can do one more, keep doing, and depends on what the data shows you the results. Your posterior are going to be adjusted according to how you collect your data. So that's the important feature, right? So the slides are posted online, so if you want to go through the computation in detail, you can do it later. But the answer is 52% over here. So again, we just went through like Bayesian inference with the toy example, like the procedure. But I want to highlight before we end the session today that the Bayesian inference is really able to take advantage of prior information, be it your own personal belief or some previously published data or like study, I should say. And a lot of times will be super useful, especially, I mean, for the mammogram testing example. If you have no idea, I wouldn't guess 50% for someone having breast cancer, right? You probably would want to rely on something that you did it before. And this is a great way or a great example to show that. And again, Bayesian inference naturally integrates data as you collect it. Yeah, especially if in a sequential manner, then you can keep updating to your posterior, to your next posterior. Okay, so it's super important to realize that if you do this kind of sequential thing, your previous posterior becomes your new prior, because that's what you saw already. That's what your inference is about already. Okay, and again, I'm going to say that the frequentist definition of p-value, like we talked about before, was slightly counterintuitive in terms of how it's phrased. But for the Bayesian approach, it's directly related to the conditional probability of the event or hypothesis being true, given what you see in the data. Okay, so we'll see that more next time, but just one more comment over here. We talked about it a little bit before as well. As you can see, if the sample size is small, then the prior is going to play an important role. So choosing the right prior, a good prior, is an important task, and we're going to talk about that throughout the semester as well. But it's a good, I think, a good reminder to start with. Okay. All right, perfect. I can end with this topic, and then so I can get the video ready. All right, so okay. So I think, yeah, we meet on Tuesday. I think on Tuesday I will try to finish the introduction. I will post the next lecture online in case we go over as well. And yeah, that's it. I think if you need help with downloading and installing R and R Studio, let me know. And make sure that you fill out the survey soon. And also create your data cam account so we can start doing that. Okay? Thank you.